All right, let's get started. So on Monday we started talking about specification, and I showed you one way to write mathematical specifications, which is temporal logic. Are there any questions from that lecture? Did you guys go back and try writing the space-wise specifications in temporal logic? Yeah. Okay. So if you have any questions about that, I mean, if you haven't done that yet, please go ahead and do it. If you have questions about the notation or the meanings of operators, things like that, do come and talk to me during office hours. Okay. So today we're going to continue with the same thread, which is talking about specifications. But today is going to be a slightly different way of writing specifications, which is actually something we've seen before. We're just going to draw state machines. So you can always write a specification for a system as another state machine. But then once you have a state machine for your actual design and a state machine for your specification, there's this problem of checking whether the two do the same thing, right? So there's a question of comparing the two state machines. And so that's going to be the main topic for today. So I want to motivate this by a concrete situation that shows up in industrial practice, which is the problem of component substitution. So oftentimes you create, especially if you think about the car industry, right? So you create a particular version of a car, and then a year later there's pressure to release a new version, right? And so what happens in these new versions? Well, there are software upgrades, and there are computer upgrades of the computer parts, and there are electromechanical upgrades, right? And then there are aesthetic things like bigger cup holders or fancy upholstery and things like that, right? But all of these are instances of substituting one kind of component for another, okay? And so at the end of the day, if you take version 1 of a car and substitute some subsystem with another component, you want to make sure that it still works the same way, right? The basic functionality is not changed by substituting components. So let's look at something a little closer to what we have in the labs in this course. So that's the Luminary microboard. Oftentimes when people want to speed up their system, improve performance, one of the things they do is let's replace the microcontroller with a different processor, right? So this board has the ARM Cortex M3 a later version in the same series is the Cortex M4. Does anyone know what these differ in? So it's actually not the size of the cache, but the M4 has a floating point unit, so it can additionally execute floating point instructions. Okay. So now let's think about this problem. Suppose I had the Luminary board, and the Cortex M4 only differs in this respect from the M3, right? It's just the floating point unit. So if I were to replace the M3 with the M4, right? And let's say the application using this was the iRobot, okay? The thing that you did in the lab. Would it still work? Yeah, Rafael?
We don't know unless we specifically know that we are not.
Okay. So, right. So we need to do the differences between the two chips. So if I were to tell you that the only difference is the existence of the floating point unit and the ability to execute these additional floating point operations, then
we know how our program exactly deals with those.
okay. Okay. So if you originally had a processor like the M3 without a floating point unit, any programs you compile down to it would not use floating point operations. Now if you have now the M4, which supports all of those old instructions plus some additional instructions, what would you expect? Should the program still work? It's reasonable to expect that the program should still work, right? Because you're not using the additional functionality. And it should interpret the original instructions in the same way as the M3 did. Okay, but there are a few subtleties. So what about timing? Right. So this processor is running at 50 megahertz. Who knows what the clock speed of the other replacement is? And if your system depends on timing, then you have to worry about that. You can't just swap in one processor for another. In fact, you can't even swap in one Cortex M3 for another if your system is timing sensitive. Okay, so it's actually fairly tricky to figure out whether it's safe to replace one system component for another, even if you knew the differences between these two components exactly. Okay, because it really depends upon how this is used. It depends upon the remaining part of the system and how it interfaces, and it depends on the software that runs on the processor in this case. So today's lecture is going to be about some mathematical principles that will help us reason about this problem. Okay, this is still an unsolved problem, right? So in industrial practice, people still don't have a good way to check for if it's okay to substitute one component for another. But we're getting closer. There's been progress in this area over the last 30 years, and so there are tools today that help you think about that. So essentially, you can think about these two processors as state machines. They're huge state machines, but basically they're state machines. And the question is, what is the difference between these two state machines? Can you replace one state machine by another? So for example, you can ask questions like, if I have two state machines, let's say finite state machines, are they equivalent, right? So are their input-output behaviors the same? Or if they're not equivalent, then does one do more than the other? Does one state machine have more functionality than the other? Okay, that is, it can, like in the processor case, the inputs to the processor you can think of are the program memory and the data the program operates on. Okay, and if you had the M3, which doesn't support floating point operations, and you have the M4, which does support floating point operations, then the set of inputs that the M3 takes is a subset of what the M4 takes, right? So in some sense, the Cortex M4 does much more than the Cortex M3. Okay, so how do we define this precisely? Okay, so that's another question we'll look at. And there's many reasons to compare state machines. So the first reason is something similar to what we had on Monday, the situation we had on Monday, which is you have a design and you want to check if the design conforms to a specification. But today, the specification that we look at are going to be given as state machines. Another application we've looked at is to check if component substitution is okay. And a third, yet another example is you might actually do model-based design, right? So rather than directly implementing your system in code, you might start with a high-level model, and you might start with a really unoptimized, slow model, right? I mean, it may just have many more states than it should, and you might want to optimize that. So reduce the number of states, maybe reduce the number of inputs, things like that. And the question is, if I have the starting model and I have my optimized version, do they do the same thing, right? The definition of optimization is that it does the same functionality, but it does it faster, right? For example, so you optimize performance, but you want to keep the correctness when you do that. Okay, so that's another question. So if you optimize a model by reducing complexity in some sense, then what is the relation between the new version and the previous version you started with? Okay, so let's take an example to think about all of these things. So let's go back to our iRobot, and we'll construct a model of the controller for the iRobot, a very simple minded model. So here in this model, it takes in one input, a pure signal level. So so level is essentially it's okay. So if this is the ramp, okay, so that's the flat portion, and this is the inclined portion of the ramp. Then if you have your iRobot here and it's oriented correctly, then level is true. Okay, so the level signal is present, or it's true when we are oriented along the ramp correctly. And if instead the iRobot is oriented at some angle, then level is not true. Okay, so that's the abstraction here in this model. All right, and the outputs that the controller provides are to the iRobot actuators. So it has two kinds of outputs: either forward, which means drive forward, or rotate, which means stay in place and rotate. Okay, so if for example the iRobot is not level, then what you should do is stay in place and rotate so that you are level, and then you would drive forward. Okay. So let's see how this is modeled here. So you start out here in this state where you're on the ramp. It's tilted, and I'm sorry. It's not aligned parallel to the ramp, so it's at some angle. So that's what the tilted mode is. And so you keep rotating in the tilted mode until level becomes true. When level becomes true, you go to the straight mode where you drive straight. Okay, and so the output, whenever you enter the straight mode, the output is always going to be forward, which is the iRobot is driving forward. And when you enter the tilted mode, the output is rotate, which means whenever you're not level, you stay in the tilted mode and you rotate until the iRobot becomes level. Okay. So that's what this model is doing. And let's assume that this is time triggered. So these transitions are taken on the tick of some clock. Okay. So that's one possible model. Here's a simpler model. So you might see in this top level model that what's really happening is whenever the sensor input says that you're level, the output is forward, drive forward. And whenever the sensor input is not level, the output is rotate, right? And it doesn't matter whether you're in the tilted mode or in the straight mode, correct? The behavior, the input-output behavior is the same. And so you might just think of creating a simpler model where you have a single mode, and whenever the input is level, the output is forward, and whenever the input is not level, the output is rotate. Okay, so now we have two possible models for this driving behavior of the iRobot. Okay, one with two modes and one with a single mode, and they are both time triggered. So they both take their transitions on the tick of the same clock, let's assume. So what do you think? Is the bottom machine is M2, the top machine is M1. So are they equivalent? Yeah. In what sense?
Well, because when we go to the second
right. So in terms of the input-output behavior, it looks like doing the same thing, correct? That's one kind of equivalence. Okay, but we'll see in this lecture that there's other kinds of equivalences that we also have. In fact, there's a sort of there's three definitions of equivalence that we look at, and they are in increasing order of strictness, right? So if the first is the loosest form of equivalence, and then a certain tighter form, and then another tighter form. Okay, so the loosest form of equivalence we'll see in the lecture is type equivalence. Okay, so the types here in these two models are simply the types of the input and output signals. Right, so here you have a single input, which is a pure signal. You have the same input, which is a pure signal, and likewise the outputs are exactly the same, and they have the same types. Okay, so if you simply looked at this as an actor, right? If you looked at the actor model of this system, then it would have the exact same actor model for the top as well as the bottom, right? So let me just draw it on the board. And so if you were to draw the actor model, you would have one input port, and you would have two output ports, forward and rotate, right? And they have exactly the same types. So this is a pure signal. Okay, so Here we're completely ignoring what's inside the box, the exact details of the state machine. We just look at the interfaces, and if the interfaces match up in this sense that you have the same input and output ports and they have the same types, then we say they're type equivalent. Okay? But as we noticed, there's a stronger form of equivalence that seems to hold for these two machines. In particular, for every input sequence that you provide to M1, you'll get a corresponding output sequence, and that output sequence will be the same as the output sequence you get down here for M2. Okay? So for example, if your input sequence is something like level is present and then absent, present, etc., right? Then in both state machines, what you would end up doing is starting in the initial state, it will generate forward. Just depending upon the value of level, you'll get a corresponding output sequence. Okay, and it doesn't matter which state machine you're looking at. So in that sense, the behaviors of the two state machines are the same. No matter what input sequence you provide, you see the same output sequence. Okay, this is known as language equivalence. Okay, and we'll get to the point of why do we use the word language. We'll get to that when we get to the formal definition. Okay, the third form of equivalence is called bisimulation. All right. The word simulation, roughly before it was adopted in the computer world, it meant to kind of fake or imitate, right? And so in computer science and engineering, the word simulation is often now used with using a simulator, right? You're basically using something which pretends to be the actual system, right? But it has the word simulation actually has a more formal meaning in computer science, which actually goes back to the early days of computer science. And it has a very precise meaning, which is you have one machine, and that machine can take the same transitions or same steps that the other machine can. Okay? So specifically, for every state of, let's say, machine M1, let's look at the tilted state, there is a corresponding state of M2. In this case, there's only one state, the driving state, such that no matter what input you get when you're in the tilted state, the outputs will be exactly the same as when you're in the driving state. So if you're in the tilted state and you get the input level, you generate output forward, which is exactly the same thing as you do in the driving state. And if you're in the state tilted and you get the input level is absent, then the output is rotate, and it's the same as in the driving state. Okay. Note, we're not talking about sequences here, input sequences here. We're talking about transitions, individual transitions. So there's a relation between this state and this state, which is that to an outside observer, these two states behave equivalently, right? And moreover, it's not just the outputs, it's also the next states. So if I go from tilted to straight, then here I would go from driving back to driving, and then any further transition I take will behave the same way. So now if I'm in the straight state up in M1 and I'm in the driving state in M2, and if level is present, again the output will be forward, and here also the output will be forward. Okay, so it's as if these two machines are going in lockstep, right? I mean, they're taking transitions. Internally, the states are different, but if you think of the machines as a black box and you can only see what's happening outside, it's just the same. Okay, so that's what bisimilarity is, and we'll come back again to the formal definition of bisimilarity. But one important point to note is that this notion looks very similar to the one we had on the previous slide, right? Language equivalence, it seems the idea is very similar. That is, the observable behavior of the state machines is the same. And in fact, for these two state machines, the specific example, language equivalence and bisimilarity are exactly the same notion. Okay? They're the same mathematical notion because both of these state machines are deterministic state machines. So for deterministic state machines, there is no difference between language equivalence and bisimilarity. It's exactly the same. But the difference arises for non-deterministic state machines. Okay, and we'll see an example of that difference later on in this lecture. All right. So that was an introduction to these three notions using this little example. Are there any questions so far? No? All right. So okay. So one thing to keep in mind as we go through is, in simulation there is this notion of a correspondence between states in one machine and states in the other machine. So in this case, both of the states of M1 map to the same state of M2. Okay, so there's this mapping which we'll call the simulation relation, and we'll get back to it when we talk about the precise definition of simulation and bisimulation. All right, so far we have been talking about equivalence. So we said I have two machines, M1 and M2, and they are type equivalent, and they are language equivalent, and they are bisimilar, right? But then the example that I showed you at the very beginning, the Cortex M3 and the M4, right? They are two different state machines, and they are not equivalent because the M4 has additional functionality that's not in the M3, correct? So we need another definition to think about that relationship, and this is the notion of refinement. So in a sense, the Cortex M4 is refining the M3, right? It's providing this additional functionality which the environment doesn't need, right? So these two state machines, if you have two state machines M1 and M2 which are not equivalent, they can be related in other ways. So for example, the state machine M2 might be what we'll call type compatible with M1, meaning that if I had originally state machine M1 and I took it out and I plugged in M2, M2 would be able to receive the same inputs that M1 did, and it will be able to provide outputs that that whoever M1 was talking to can still receive, right? So it's compatible in that respect. Okay. The second thing is that M2 might be a special kind of M1 where it can only provide output sequences that M1 can provide. Okay, this is called language containment. So we'll get to that as well. And the third aspect is called simulation. So in simulation, what happens is one machine can imitate the other, but not necessarily vice versa. Okay, and so in this case, if M2 is a specialization of M1, M1 can imitate M2, but M2 may not be able to imitate all behaviors of M1. All right. So these are the exact symmetric notions as we had in the previous three slides, except now the machines are not necessarily equivalent, but they refine each other. Okay, so let's define these more precisely. So the first kind of refinement is called type refinement. Okay, and here's an example. Let's say I have machine M1. So we're talking about types, so we don't really care about what's inside the box. We're looking at the interfaces. So machine M1 has two ports, X and W, sorry, and it has one output port Y. And machine M2 has only one input port, X, and it has two output ports, Y and Z. Okay. Now let's think about whether you can replace M1 for M2. M2 for M1, the other way around. So let's say you have a system that uses M1 and you want to instead plug in M2 for M1. Okay. Let me just define, so that's the question we need to think about. Let me define the notation additionally here. So here when I say X colon Vx, Vx is the type of X. Okay, and let's think about the type of X as the set of all values that X can take. Right. So for a pure signal, it can take values present or absent. Okay. So V of X is the set of all values X can take. V of W is the set of all values W can take, and V of Y is the set of all values Y can take. Okay. The same thing down here, except we have possibly different types: V prime X, V prime Y, and V prime Z. And the input ports of M1 are P1, and the output port is the set of output ports is Q1, and likewise you have P2 and Q2 there. Okay, so that's what we have here. Okay, so let's just ignore the stuff on the right for now. Let's just think about this example. Okay, so when can we plug in M2 for M1? Okay. For a second, let me just say that forget about the primes. Let the primes be this. Let's just delete the primes. Okay. So the type of x down here is the same as the type of x up here, and the type of y down here, let's say, is the same as the type of y up here. Okay. So let's consider that simple case first. So is it possible for us to substitute M2 for M1? Yeah? If the output is independent of W. Okay. So in this case, M2, the output, if you substitute M1 by M2, the output of M2 definitely is independent of W because there is no input W, right? So here all I'm talking about is type compatibility, right? So in terms of the types of the output, is there any difference between M2 and M1? Right? If we assume that Vy is the same as, there's no prime, so V prime Y is the same as Vy, there is no difference, right? The output type of Y down here is the same as the output type of Y down over here. So in general, you can, in this case, you can replace M2 for M1, okay? And the way to think about it is that let's say the environment of M1 here, which is providing the inputs X and W, is going to continue to provide the same inputs to M2, right? So the same inputs will come down here, but M2 just ignores one of them, right? It doesn't do anything with the input W. And M2 will generate additional outputs probably, so it can generate Y, but it can also generate Z. But the environment of M1 will not use that additional output. Okay, so the environment of M1 only needs Y, and M2 is able to provide Y of the same type. Okay, so in this case we can substitute M2 for M1 because the input ports are a subset of the input ports of the original machine, and the output ports are a superset of the output ports of the original machine. Okay, and that's what we have here. So M2 is a type refinement of M1 if its input ports are a subset of the input ports of M1, and its output ports Q2 are a superset of the output ports of M1. Okay. Additionally, here we have relations between types. So what this is saying is, for every input port of M2, the set of values that input can take have to be a superset of the values that the corresponding port of M1 could take. So for example, here if X was Boolean, it can take values 0 or 1, and here it can take a value that's 0, 1, 2 or 3, right? Then the set of values that M2 can accept is a superset of the values that any environment of M1 will provide. And so if you plug it in for M1, 0 and 1 is still a valid input to the resulting machine. Okay, and similarly for the outputs, it's going to be the other way around. So for every output port of this machine, the set of values of that output port is going to be a superset of the set of values of the replacement machine. Okay, so this means that if I plug in M2 for M1, any output value M2 will provide will be acceptable to the environment, right? So if for example you had something, if this didn't hold, like let's say Y was Boolean, took 0, 1, and here this took 0, 1, 2, 3, and now you replace M1 by M2, and suddenly the output of Y is 2, right? Whatever module is connected to M1 here, it's not going to be able to interpret that value correctly because it was only designed to receive a Boolean input. Okay, so so the input types that M1 accepts have to be a bigger set than the input types M1 accepts, and the output types M2 produces have to be smaller than the output types that M1 produces. Okay. So if M1 is an adder, yeah. So if M1 is an adder, and so it took x and w, and y was x plus w, right? And M2 was, let's say, an incrementer. So it took an x, right, and it just increments it and produces y by 1, okay? And let's say this is, for simplicity, vy is an integer, and v prime y is also an integer, okay, and the inputs are also integer values. Then M2 is a reasonable, from a type viewpoint, it's fine to substitute M2 for M1, okay? It doesn't have the same functionality, exactly. It's a good point. So far we're talking only about types, right? This is a very low level notion of equivalence or refinement, correct? But as you correctly observed, if M1 was an adder and M2 was something like an incrementer, you just can't replace M2 for M1, right? Because it will change the meaning of the resulting system, correct? The types might be compatible, but it just changed the meaning, okay? So all we are looking at here is, can I replace one module for another, one state machine for another, without causing a type conflict, right? And you can do it if these 4 properties are satisfied. Okay, that's all we're saying. But that's clearly not enough. Okay, so here's another example from earlier in the course. This is the garage counter, right? So you have the counter goes from 0 to m, and it counts up whenever a car enters and no car leaves, right? And so if you look at this system, the input ports are 2 signals up and down, which are pure signals, and the output port is just the count, and the count in this case goes from 0 to m. So if you get a sequence of inputs like this, right? So in this case, up and down are both present, then nothing happens to the count. If they're absent, nothing happens. But if up is present and down is absent, then you count up to 1, etc. Okay, so that's an execution trace of the system. So now one possible type refinement is something that has to do with the value of m. So let's consider a particular instance of the garage counter where m is equal to 99, and then you replace it with another garage counter m2 where m is equal to 90. So all that's different here is the number of internal states depending on the value of m and the kinds of outputs it can produce, obviously. Okay. Now if you look at it from a purely type viewpoint, then M1 is a refinement of M2 because they have exactly the same types, right? So whether you have M1 or M2, the inputs are going to be up and down, and the output will be count, right? And in the case of both M1 and M2, the input types are the same, okay? And the output types are different, right? So for M1, the output type of count is the set 0 to 99, and for M2, the output type of count is the set 0 to 90, right? And the output, the set of output values of M2 is a subset of the set of output values of M1, right? And so this is the condition that we had here. For every output port, the set of output values of M2, the replacement, has to be a subset of the values of M1, right? So all of those conditions are satisfied. So M2 is certainly a type refinement of M1. Okay. Now, is that for this garage counter example? I think for the adder incrementer example, it was quite clear that you can have situations where you can't replace the adder by an incrementer, right? But what about the garage counter example? From the functionality viewpoint, is it okay to replace M1 by M2? Yep. Okay, good. So what it'll be correct in the sense that you'd let a car in only if there is a space, right? But there will be 9 unused spaces, right? Because your counter only can go up to 90, and so if the system that's allowing cars in doesn't allow it once it reaches that count, you'll have this additional 9 spaces which won't be used. Okay, so so in this specific context, it seems okay, but in order to reason about that, it wasn't just type compatibility that we used, right? We used some other notion, and so that's something that we have to reason about, and we'll use the notion of language equivalence or language refinement to think about that. So so now let's consider another situation here with the same example. So we had this is the explicit state representation of that garage counter, and remember we had another representation which was an extended state machine, and here you have apart from the inputs and output, you have this variable C. Okay, so in this case, we know from our previous lecture that these are just 2 representations of the same state machine, right? Certainly the input output type signature is the same, right? It looks like that. You have 2 inputs up and down, both pure signals, and 1 output count, and count goes from 0 to m. So the types are exactly the same in this case, right? And in fact all the input output behaviors will all be the same. It's just a different notation for writing the state machine. Okay, let's look at a slightly different example. So this one here is what we looked at previously, and we reasoned about the fact that the input output sequences of these 2 machines are the same. Okay, so this is language equivalence. So to define language equivalence precisely, we need to go back to the same notion we looked at on Monday, which is what is an execution trace of a state machine. So in this case, an execution trace is again a sequence of input, state, output triples, right? So that's Q0 is input, state, output at step 0, and then at step 1, step 2, etc. Right? So the language of a state machine, so if a state machine M, the language L of M is simply the set of all behaviors, all execution traces that the machine can generate. Okay, so you assume that you can throw any input sequence at this machine, right? So if let's look at this case here. If you have this machine where you have a single input port X, and X is a pure signal, let's say, then the set of all input sequences would be the set of all sequences, infinite length sequences, where every element of the sequence is either present or absent, right? And so one sequence can be present, 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 present ad infinitum, or you can basically replace present with absent anywhere, any number of times, and you'll get all possible sequences. Okay. So that's a set of all inputs. So the thought experiment you should have while thinking about the language is that you have a state machine, you provide all possible input sequences, and that generates all possible output sequences, and you put those together along with the state, and that defines your language. Okay. In particular, for this lecture, what we'll do is we'll define the trace to be a little bit simpler than what we have on this slide. We'll define the trace to only have the input and output, not the state part of it. Okay. So yeah, question.
So this is so that the second machine can sort of nest inside the first machine's state. If the second machine only produces the exact same set of outputs as the first machine, but only for the input space of the first machine. What if the second machine has one?
Okay.
But you don't see it, because you only receive the inputs that the first machine receives.
That would be okay, right? So that's basically the implicit assumption there is that you will only use machine 2 in the same environment that machine 1 was plugged in, right? And so that environment is only going to provide the inputs that machine 1 could get, right? And so with that additional context, it's okay to replace M2 for M1. Okay, so so here's the notion of a trace in general. What I'm going to do for this lecture is you basically assume that Qi, every element of that sequence in the trace, is simply the input and the output at that step. Okay, so Qi is just the pair xi yi, and your trace is simply going to be the sequence Q0, Q1, Q2, etc. Okay, so this is the notion that we'll use for this lecture. A trace is simply an infinite sequence of inputs and outputs, and we won't consider the state. Okay, so all right, so now this is a notion that you have to fix in your mind. The language of M is a set of all behaviors, all input-output traces. And now the definition of language refinement is that M2 refines M1 if the language of M2 is a subset of the language of M1. Okay, so the language of M1, the language of a machine in general is an infinite set, right? Because you have an infinitely long sequence, and every element of the sequence is some combination of input-output values, right? And so you can generate infinitely many of these infinitely long sequences. So the language of a state machine is an infinite set. So what we're saying here is that M2 is a refinement of M1 if the infinite set corresponding to the language of M2 is a subset of the infinite set corresponding to the language of M1. Okay? Now it's possible to have, I should clarify one thing. In general, these are infinite sets, but it's possible to have degenerate state machines which only generate a single behavior, right? But in general, the thing you should be aware of is this is set containment between infinite sets. Okay, so pictorially, if you like Venn diagrams, then the idea is that you have a set of behaviors for the language of which correspond to the language of M1, and you replace it with M2 if the set of behaviors for M2 lies inside the set of behaviors for M1. Okay. Now, language refinement is actually pretty a pretty powerful notion, and it's useful for all deterministic systems, which is all systems in practice that you can construct are deterministic. Non-determinism is a useful modeling notion, though. And what happens is when we look at non-deterministic state machines, sometimes language equivalence is not enough to reason about the fact that one state machine can do more than another one. Okay, and here's a simple example of that. So here's a state machine with a single input x, which is a pure signal, and output y, which takes two integer values, either 0 or 1. And so what machine 1 does is it starts off in the state A, and if x is present, it outputs 0, goes to B, and then B is a state from which you see non-deterministic behavior, right? So if x is present in B, you could do one of any of these two things. You could either go to state C and output a 1, or you go to state D and output a 0. Okay, and I think this is only the relevant behavior we want to think about. So even though this machine could, for example, loop forever in state C and D, let's just ignore that for the time being. So what's the set of all behaviors of the state machine M1? The set of all input-output sequences. Okay, so it will be, there's two possible sequences. I'll write the sequences inside parentheses. So you have present, the input is present, and the output is 0. And then you could have x present and output 1. That's one sequence. Or you'd have present 0 and present 0. Right? So that's the language of M1. Okay, now let's look at M2. So M2 has the same type signature, same input, same output, but the transition structure looks different. Here the non-determinism is at the very initial state. So you start off in state E, and if you get an X, then you can either go to state F or to state H, and in either case the output is 0. Okay, but once you made the transition, then you made a choice, and so from F there's a single transition out to G on an X, and the only output you can generate is a 1, and from H there's a single transition to I, and the only output you get for that transition is a 0. Okay, so what's the language of M2? Same thing, right? So you have again two paths. Along the top path EFG you have present 0, present 1, so the same as the first sequence there, and then you have present 0, present 0, which is the same as the second sequence. Okay, so they are language equivalent. L of M1 equals L of M2, but they are different in a certain way. Okay, so can somebody tell me what's the point of difference between these two machines? Right. Okay, right. So the non-deterministic choice in the first machine is one step later than it is in the second machine, right? So now if we are executing these two in lockstep, for example, so X is present in the first step, so this machine goes from A to B, but this machine M2 has to make a choice whether to go from E to F or E to H. So let's say M2 makes a decision to go from E to F, right? So now the M1 is in B and M2 is in F, and now if you get again X present, M1 can decide to go to D and output a 0, but M2 is stuck, it has to only output a 1, right? So if you think of a game played by these two machines where one has to match what the other does, right? Then because M2 M1 has deferred its choice, right? M1 can exhibit a behavior later which M2 cannot match. Okay, so so that's what we mean by this statement. We say that M2 is a simulation refinement of M1, but not vice versa. Okay, meaning that M1 can do whatever M2 any step M2 can do, because it defers its non-deterministic choices later, but M2 cannot imitate M1. Okay, so so now if M1 is my specification, okay, then in some sense M1 is more powerful than M2 here, because it defers the non-deterministic choice to later, right? So M1 can match any step of M2. So if M1 is my starting model, it's okay to refine it down to M2, because any system that uses M1 can also use M2. The set of behaviors that M2 produces can always be matched by something M1 produces. So if everything M1 produces is okay, then certainly everything M2 produces will be okay. Okay, so that's the relation between these. Okay, so you can let me say that once more. You can substitute M2 for M1 because M1 exhibits more behaviors than M2. Okay, and if you've used M1 in a system and that system is correct, then it's okay to take out M1 and put M2 instead, because you know everything that M1 did, M2 whatever M2 does is a subset of what M1 did, right? And so M2 cannot add any bad behaviors to the system. Okay, the system is going to be correct. Now the other way around, if instead you thought about replacing M2 by M1, then that may not be okay, because I mean basically you should think about what is non-determinism, right? Non-determinism is a modeling technique. It's a way of just constructing a model. So you could think that the environment of M1 and M2 is a scheduler which resolves the non-deterministic choices. It tells the machine how to move, right? And so if my scheduler, if M1 worked correctly with the scheduler, then so will M2, because any behavior M1 produced, no matter which way the scheduler made M1 go, M2's behavior is going to be a subset of that. But on the other hand, if I started with M2 and the scheduler basically makes a decision of either go here or here, so if the scheduler fixes either make the transition on the top or make the transition on the bottom, and let's say for M2 that non-deterministic choice at the first step was okay. For M1, because the choice is deferred, there's no way you can reason about the same thing. There is a behavior of M1 which you would not have seen when M2 was plugged in with the scheduler. Okay, so a convenient way to think about simulation is really as a game between these two machines. So to say that M1 simulates M2, what we're going to do is construct what's known as the simulation relation. So the simulation relation is a set of pairs of states, one of M2 and one of M1. Okay, and so this is going back to the idea we had earlier, which is remember for the iRobot example, you had two states in the first machine, tilted and straight, and you had one state in the second machine which is driving, and we mapped the two states in the top machine to the single state of the bottom machine, right? That mapping is the simulation relation. And so what we're going to do is now construct the same mapping between these two machines. Okay, so to start with, we're going to just list out the set of states. So S1, the set of states of M1 is A, B, C, D, and the set of states here is E, F, G, H, I, right? So so now both machines start off in the initial state. Okay, so the initial state of M1 is mapped to the initial state of M2, and from an observational viewpoint, these two seem the same, because when you provide an X in this initial state, you'll see an output of 0. Okay, it doesn't matter which initial state you start with. If you provide an input, you get the same output. And now for the next step, so let's say you get an X is present, this moves to B and this moves to either F or H, right? So the question is, if M1 simulates M2, does B behave the same as F, and does B behave the same as H? Okay, so let's look at the first case, so B and F. So in this case, if I provide an X in B, it can either present a 0 or a 1, right? And if I provide an X in F, then it'll generate an output of 1. So for every transition out here, from every transition out of F, there is a matching transition from B. Okay, so in this case, the transition from F to G is matched by the transition from B to C. Okay, and so because of this, the state of M1 B simulates the state of M2 F. Okay, so we can add F comma B also into our simulation relation. If you look at the second possibility, then here as well, every transition out of H, which is only this one from H to I, can be matched by a transition out of B. Okay, which is from B to D. And so again, the state B of M1 can simulate the state H of M2. And finally, if you look at these two states, then in both cases, for this example, they're dead end states, right? No transitions coming out of them. So you can reach C from B, and so that matches it to G, and you can reach D from B, and that matches it to I. And so at this point, we've constructed a correspondence between the states of M1 and states of M2, okay, such that for any pair of corresponding states, the state of M1, which is the second element, behaves like the state of M2, which is the first element. So for every pair here, the second element of the pair can imitate the first element. It doesn't. You can't tell if you're in B or F just because every transition out of B is going to behave just the same way as every transition out of F. Right? So so here M1 simulates M2. Now, on the other hand, if we try to do the converse, which is to look if M2 can simulate M1, we'd fail at some point. Okay, so so let's just do that as an exercise. So the way that simulation is typically constructed by automatic tools is you take the cross product of the states here and the states here. So that's going to be 4 states here and 5 states here, and you take the cross product, which is going to be 20 possible pairs, right? And then you basically cross out the pairs which don't match. So pairs of states in which one state looks different from the other, in the sense that if you provide the same input, you generate different outputs, or if you go to different states from which you generate different outputs. But we're not going to do that because it'll be too tedious. So I'll do something simpler, where we'll start with states that do look the same. So if you look at G and C, it seems similar, and if you look at H and if you look at D and I, they're both dead end states, so they look similar. Okay, so so I should list first and DI, and then if you look at state F, then from F you go to G, and from B you go to C. So the question is, does F simulate B? And the answer is, the way you reason about that is you look at B and you look at all possible transitions out of B, and you check if F can imitate that, right? But in this case, F cannot imitate B because it can only do the first transition but not the second, right? So we would like to add this pair to the simulation relation, but we can't because there's a single transition out of F, but there are 2 transitions out of B, and so F cannot match B. And likewise, if we try to reason about whether H can replace B, right? So whether you can have this pair BH, again you can't add it in the simulation relation because H has only a single transition. It can't match both of the transitions of B. Okay, so at this point we know that the state B here cannot be simulated by anything in this state machine, and that would be okay if B is not reachable from the starting state, if B is some state dangling off on the side. But in this case, B is certainly reachable from the starting state, right? And therefore you can't have anything of the form A, you can't have anything in a transition relation of this form, A comma whatever. Okay, so what happens basically is that you simply can't construct the full simulation relation, that is not all states of M match to some state of M2, M1 match to some state of M2, and therefore the simulation relation, you can't demonstrate that that every state of M1 is simulated by some state of M2, therefore there is no simulation. Okay.
So you get the same thing if you start from the left. If you start from the left, you have states A and E, and the number of transitions differs.
When you start from the left.
So if you try to match up A and E.
Yeah.
So the number.
Oh, you start from the left. Yeah.
Sorry.
Right.
So if you start from G and C.
Correct.
If we go the other way.
Yeah.
If you start with A and E.
Yeah.
The number of transitions after the state differs. So what you said that automatically.
Yeah. So the thing is, when you start from going from the left to right, from the initial state onwards, you need a bigger look ahead. So in this case, because C and D didn't have any outgoing transitions, it was easier for me to start from there because I could say that they match up, but then if I cannot match B with either F or H, I can stop right there. Okay, but when I go from left to right, then to see if A matches E, I have to have to go not just one step, but in this case it's simple, but in general I might have to go multiple hops to see where the non-deterministic choice splits, right? Where there's a difference between M1 and M2. So that's the reason why I started from right rather than left, but you could go either way.
So why can you explain again why you have to trace more than one step?
Yeah, so basically here's the definition of simulation, okay? And I have the formal definition on the next slide, but the real definition is state A simulates E if the immediate behavior you see is the same, that is on any input you get the same output, and from whichever state you reach, the infinite behavior that you will see will be the same. Okay, that's the definition of simulation. Now, the first part is okay. If you start from A and you go to B, then that matches the observed behavior of either of those two transitions. But once you make this transition, the infinite behavior you see after that point will not match the infinite behaviors you can see from B onwards. Okay? Yeah, Purva? Okay. Okay, so the question is, what if H had an outgoing transition of this form? You get an X and the output is 1, right? So in that case, what do you think? Would M1? Would M2 simulate M1? Yeah. It does. Yeah. So the answer is it does. I mean, it would be in that case. H would be symmetric to B, right? The behavior of H would be just like B, right? On an X, you can either go to this state with an output of 0, or maybe this state with an output of 1, right? So the question, let me just repeat it for everybody else. The question is, suppose I add another transition from H to G, sorry, which is labeled with X/1. In that case, M2 does simulate M1, right? Because this state H now has the same non-deterministic choice that you have in B. Right?
Sorry, don't we need another transition from F to I to that side okay, but still the top side is not okay. We need a transition from F to I.
Oh, that's right. Yeah. So I stand corrected. You're right. So there should be two transitions. Both F and H must behave like B. Okay. Okay. So I think these are all good questions. Let's go to the definition, which looks complicated, but we'll walk through it, and then we can reason about those two. Okay. So so let's say you have these two machines, M1 and M2, and M1 is a phi tuple. So let me refresh your memory. This is the set of states, inputs, outputs. That's the update function, and that's the initial state. And M2 is again states, inputs, outputs, update function, and initial state. Okay, and at the minimum, M2 must be a type refinement of M1. Then we say that M1 simulates M2 if you can compute a simulation relation, so a set of pairs of S2 and S1, where the initial state must be in the relation. So what this is saying is that the initial states they look the same from an observational viewpoint immediately and for all future behaviors, and then for every other pair of for any pair in the simulation relation S2 comma S1. Okay, so let's say this is S2, and you have another state. This is a state of M1 S1. Now, for all possible inputs you can get in S2, right? So this is for all I in I2, and all possible next states. So from S2 onwards, depending upon which input you can get any of these could be your next state, S2 prime, and you can get a corresponding output and going to that state. So this is saying for all inputs that I get for machine M2 and all possible next state output pairs, there should exist a matching transition here. Okay, so there should be, for every transition up here, there should be a matching transition down here. Okay, this is to S1 prime with output O1, such that these two states look the same. So what we're giving a recursive definition. We're saying S2 comma S1 belongs to the simulation relation if and only if, for this picture, S2 prime, S1 prime also belong to the simulation relation, and the outputs that are generated here are going to be a superset of the outputs you get in the top picture. So O2 is a subset of O1. Okay. So what we are saying is, suppose I'm in this pair of states. I look at all possible next states in both machines, and if those next states behave the same, and if the output I get in going to those next states is compatible, then these two states are deemed to behave the same. Okay, and if you think about this as a recursive definition, then one way to compute the simulation relation is as I did, which is bottom up. You go from the states that are furthest from the initial state, and you go work your way backwards. So in this picture, we started off with G and C, right? And then that would be your S2 prime, S1 prime. So if that's in the simulation relation and the outputs are compatible, then we try to conclude if the state that is one step away is also compatible. Okay, and that holds if all next state pairs S2 prime, S1 prime of S2, S1 have that property. Okay. So now let's go back to the question that was raised, which is, suppose you have a single transition from H to G, which is labeled with X/1, right? Then does M2 simulate M1? Okay, and so in that case, if I consider, what must happen is H must be able to simulate B. But again, also F must be able to simulate B. So if you look at H comma B, so if S2 was, let's see, so here M1 is simulating M2, and so maybe I should, let's forget about these labels M1, M2 because it's inverted here, but let's just think about the state machines. So the question I'm asking is, I have state B here, and the question is, can state H simulate B? Okay, and so in this situation for B, there's two possible transitions you can make. You can go from B to C and B to D, and you have X/1 and X/0. Those are the two labels. And then down here from H, you can match this transition if we had the original transition from H to G, and you can match the second transition X/0 if you have the additional transition from and you have the transition from H to I, right? So the state B can be simulated by the state H, okay, and all of these properties hold. But the next question is, so state B is simulated by state H, but does that mean that state A is simulated by state E? Okay, so now in order to reason about that, so if this is A and this is E, then I need to look at both next states of A, which is in this case only one, there's only B. And then here for M2, there are two possible next states, which is going to F and H. and the labels should be x/0 on both, right? So now the question is, so if I have the transition from A to B, can I mimic that with the transitions from E to either F or H? Okay, so here I can certainly go from A to B and E to H, and I know that B comma H is in the simulation relation, right? So so this works out. So if B comma H is the simulation relation, and so if additionally if F comma B is also in the simulation relation, then I know that A comma E is in my simulation relation. Okay, and so now we need to go and check if B comma F is in the simulation relation, right? Now in this situation, if I simply had just this one transition from F, then B comma F will not be in the simulation relation, right? Because B has two steps and F only has one step. So in order for that to work out, you have to, as was pointed out, you have to add this additional transition from F to I, and labeled with x/0. And if you have the additional transition, then you would be able to add B comma F to the simulation relation, and then you would have both B comma F and B comma H in the relation, and therefore A comma E would be in the relation, and therefore one machine would simulate the other. Okay. All right, so that's the formal definition of simulation. Was there another question? So you could, if B behaved the same way. So let's think about what we're doing here. So I want to mimic every behavior of A, not just the first step, but every future step with something here. Okay. Now suppose I said I'm going to match it with the top transition to F. I can't match the future, right? So this requirement, this particular requirement that the next states should also be in the simulation relation, this is saying that the next states will behave the same from here onwards, right? So that's why you can't do it. Okay, so we have about 5 minutes, so let me talk about bisimulation as well. So bisimulation is a stricter form of equivalence, and in this case it's not just, the direction is not just one way. So it's not just that you want to match every step of M2 with a step of M1, but you want the other way to also hold. Every step of M1 should be matched by a step of M2. Okay? And so the tricky bit about bisimulation is that it's possible to have two machines such that M1 simulates M2 and M2 simulates M1, but they are not bisimilar. Okay, and here's an example. So this is the same M1 that we had earlier, and this is M2 where we've just added this edge. So we've added something that looks like M1 at the bottom, right? So you add this additional 3 states which look exactly like this particular structure in M1. Okay. Now, so clearly, in this case, let's see how it goes. So M2 has additional non-determinism, right? So every step of M1 can be mimicked by a corresponding step of M2 here. So, for example, going from A to B, M1. Let's see. So M2 can take this step, which corresponds to this particular step here of M1, and then from state J, it can generate any one of these two outputs, just like how B would behave, right? So B would be simulated by J, and because B is simulated by J, A will be simulated by E, right? And then this part. So we know that M2 can simulate M1, unlike the previous example, and we also can reason about the fact that M1 simulates M2 because irrespective of where M2 goes, like if M2 goes down here, then M1 and M2 are exactly the same. They behave exactly the same, and if M2 goes to one of these two states, then also M1 can match its behavior. right? So in this case, if I just look to reason about whether M1 can simulate M2 or M2 can simulate M1, that holds. But the question of bisimulation is a little bit different, which is for every step, at every step, one machine should be able to simulate the other, okay, and vice versa. Okay, so in what happens in the bisimilarity relation is you have the requirement of simulation, which is this thing up here, and you have the same requirement going the other way. Okay, so in particular here for this example, if I were to construct a relation here, then let's see, if we started out in state, what's a good, this is a pretty confusing notion, so even I get confused now again. So let's say if you start off in A and E, and you make a step in A, then for every step of A, there is a next step in M2, such that it can mimic that. Okay, so that works out. But now if I take a step in M2, so if I take a step in M2, then okay, so the notion of bisimilarity is, I think, it's best illustrated in this first initial state. So if it's the effective notion is for every possible next state that you see in M2, there has to be a corresponding next state in M1 which behaves the same. Okay, and for here, for example, if I went from E to F or E to H, that would not be the case, because going from A to B in M1, you would in M2 you would not be able to mimic any further step of M1. Okay, and so that's so bisimilarity is a stronger notion where you have to be able to have both machines, no matter what non-deterministic choice they make, what transition they take, they have to be able to remain in lockstep throughout. And in this case for M2, if you take one of the top two transitions, you cannot match any future step of M1. Okay. Okay. So maybe we'll revisit this next time in the beginning of class, and I think that's about all I want to say. So let me just summarize by making the relation between simulation and trace containment. We talked earlier that we have these three notions of equivalence, right? Type equivalence, language equivalence, and bisimulation. And we have the same kinds of relation between trace containment, which is weaker than equivalence, and simulation. So if two machines are such that M1 simulates M2, then you get trace containment for free, meaning that if according to the simulation notion, if you can replace M2 for M1, then you can also do that according to the language containment notion. Okay, so if M1 simulates M2, then the language of M1 has more behaviors than M2. So the language of M1 is a superset of the language of M2. Okay. All right, let's stop here for today, and we'll revisit this again at the beginning of next class.